This is my lab for circuits for physics 2. So for the introduction, the purpose of this lab is to use the physical principles of conservation of energy in order to predict the behavior of circuits. This is to be done through the use of an online model using multimeters to measure values of current and potential differences. For the results, the actual values of current and voltage from the model closely match those of the formulas. And in an RC circuit, the magnitude of current is time dependent based on exponential equations. So some fundamentals: the conservation of energy and charge formula, which is delta V1 plus delta V2 plus delta V3 plus delta V4 is equal to 0. Ohm's law, which is equal to V is equal to I times R, and capacitance is C is equal to Q divided by V. Some assumptions for this lab is resistance of wires is negligible, resistance of emitter is negligible, as well as EMF is equal to delta V cap plus delta V resistor. So for the first simple and open circuit, of course this system is just a circuit, surroundings is just the environment. The circuit consists of two 1.5 V batteries, two resistors, one at 47 and one at 100 ohms, and then two ammeters. The predictions for this is I1 is going to equal to I2, as well as 47 plus, of course, the entire resistors is just going to be 147 ohms, and I is equal to delta V divided by R, which in this case would be 0.02 amps. And the results is the same, 0.02 amps. And then replace one. I'm going to voltmeter readings is delta V is equal to 3 volts, I is equal to 0 amps. The open circuit with no current and potential difference across opening equals that across the power source. The next circuit is a closed circuit. Some potential difference readings is B to A is equal to 3 volts, C to B equals to 0, D to C is equal to negative 0.96, E to D is equal to 0, F to E is equal to negative 2.04, G to F, H to G, and A to H are all 0. For the delta V round trip is equal to 0 volts, which this follows the loop rule. I is then equal to 0.02 amps. The ammeter reading doesn't change throughout the process, which means the voltmeter has very high resistance, no current flows through it, and the path is essentially altered. The potential graph is shown here. You can pause to view it if you need to. For the next circuit, a parallel circuit, which is connect ammeter and parallel with a 100 ohm resistor, the current increases from 0.06 amps since less current comes in contact with the 100 ohm resistor, which is again just I equal V divided by R. R 47 ohms, which is equal to 48 ohms, R 100 ohms, which is equal to 102 ohms, R wire is equal to 0 ohms, and R ammeter is equal to 0 as well. For this, the current is higher than expected due to the low precision of the ammeter. For the next and final circuit, which is the RC circuit, also I tried to get a better picture of it. For some reason, it kept coming out blurry. The circuit, which is a 10 ohm bulb, a 20 ohm bulb, 9 volt battery, and 200 mF capacitor. The battery attached to the 10 ohm bulb and capacitor in series circuit, the bulb starts off bright, then decreases until burning out, which is also just charging. And then the current burns from maximum to 0. So if the battery disconnected, the bulb once again lights up, then decreases in luminance. 10 ohm bulb, which would be 10.3 seconds charging and 12.2 seconds discharging, and the 20 ohm bulb, which was recorded at 17.5 seconds charging and 22.5 seconds discharging. Here is the time dependency graph. You can also pause to view this. For an This is for a 9-volt battery, 200 mF capacitor, and a 30 ohm light bulb. And there is the ln delta V formula down there at the bottom. So the data recorded, the experimental RC, the slope of the graph was found to be negative 0.1667, which is also equal to negative 1 divided by RC, which is also equal to 6 seconds, around 6 seconds. The 200 mF times 30 ohms, which is also equal to 6 seconds, or around 6 seconds. Sorry, I am very tired. The calculated RC matches the actual value for the RC recorded. So finally, for the discussion, what if you were doing this lab in real life and used an actual ammeter instead of an ideal simulated ammeter? What's different about the real ammeter, and how would it have affected the circuits you hooked it up to if you did this lab with real circuit components across the virtual circuit? Link above, that's from Canvas. And see if you can determine how it behaved differently from the real ammeter you use. Since a real ammeter has non-negligible resistance, the currents would slightly be lower. What if you were doing this lab in real life and used a real battery to charge a real capacitor with no resistor in the circuit? How quickly would our ideal model predict the capacitor reach full charge? Would this prediction happen in real life? If you are completing a lab with real circuit components, use an ammeter to measure how long it takes to charge the capacitor, blah, blah, blah. Discuss why the measured time is different from the predicted time. The capacitor would still charge and discharge very quickly, but not instantaneously as it did in the simulation where the wires had zero resistance. In real life, the wires have a non-negligible amount of resistance.